I'm standing in front of you as a co-founder of Trinscality, which is a ETH spin-off that focuses on digital twins and the creation for transportation networks. Before I start, let me just put this clear, right? Digital twins, everyone has their own definitions of what it is, etc. We can have a lengthy talk afterwards, happy to. And also the second thing is when we talk about transportation models, I will be covering mainly the operations part of it and no, let's say, future magic ball, let's say, predictions what will happen in 2050. Sorry. Until now, until the 3 years that we've been in business, we've been quite proud to be able to acquire projects and actually sell our services to a multitude of actors in the transport sector. First and foremost, Transport for London as our first customer. Then also a very good customer of ours is the highway authorities of Switzerland, but also the city of Zurich, city of Geneva, Basel, but also Salzburg and Munich, for example. And what we essentially do is best illustrated by the following animation. What we try to do is to replicate whatever you see moving in this picture, right? And to replicate this in a digital world where we can do 3 things. And remember, I'm trying to do anything that covers operations only. So we're trying to have first a way of monitoring of what happens. So let's say a Google Maps plus, right? Doesn't only give you green, red, and yellow, but gives you flows and speeds, etc., on all of your links. The second thing that we're trying to do is essentially to be able to answer the question, what will happen if we close this bridge here? Something that traffic simulations have been able to do for a long time already, but calibrating them for such large networks is a topic that is probably still not finished, right? And the third topic is really where I would say that whole digital twin comes into play, which is how can we run all of this in real time to proactively control what's going on in our city from a traffic perspective. So this is really where we close the feedback loop and where we connect the digital world with, let's say, the operations of our city, so really becoming a digital twin. When I zoom out quickly, I think these are topics that were mentioned by my previous speakers already today. So I'll go very quickly through, right? Increasing urbanization, net zero targets all over the place. They create a lot of changes in the infrastructure. Paris, we heard as an example, Barcelona, also Geneva might be mentioned here and there. This creates changing mobility requirements, and essentially the question here that we get from many of our customers is, can we remove a lane for cars and add it as a bicycle lane? A classical e-bike city question. What happens if we close the main bridge for a month? Or how can we alleviate the traffic congestion caused by this road closure? And let me explain to you, and I think Kai gave already kind of a hint at how this is done nowadays, slightly slow and also frustrating sometimes. So you come up with a problem in your city, you're trying to solve it. So essentially you award a project to a consultancy. It takes relatively long, 3 to 6 months if you're lucky, that's quite fast already. And then there's some completion and execution. Most of the times these consultants also use some kind of traffic simulator in the background. But what we're trying to do is essentially really changing this paradigm of fast prototyping. So we're aiming to have a tool which identifies, the problem identification is still part of the customer's job, but then you have a fast way of fast prototyping what kind of scenarios you would like to look at. And this will become clear in just a second, what I mean by that with this kind of short sale video, let's call it, right? I'm allowed to do a little bit of sales given that I'm not in academia anymore. Please bear with me. So essentially what you see here is the web app that, for example, the city of Zurich or city of Geneva would log into. They would create a project which could be a construction site, and you basically create your scenario here. And until now, everything looks like a classical traffic simulator, except that, and this is the most important part, that it's very easy to use. There's 3 things that you can do. The first thing is close the lane. The second thing is basically change the speed, and the last thing that you can do is change the turning movements that are allowed. These are the 3 things that cover, let's say, 80% of the typical scenario jobs that people do. You can then select basically from when to when you're interested in to actually look into this scenario and you run the simulation, and this really runs in real time, so it's not running it's very fast in the background. I'll show you in a second what kind of simulator we're using in the background. And essentially you get back to this map here, which probably reminds you a little bit of Google Maps, and that's exactly the idea, right? So we're trying to have a tool which is extremely simple to use, which is a professional tool for non-professionals, right? So that you do not need to have a PhD in traffic simulations or digital twins or whatever in order to use and calibrate these type of models. And you can even in the end basically download, let's say, a little report where it tells you you have changed this and this is your impact, etc. This is really something that the city of Geneva, for example, just ordered this and will be using starting in March. So it's what I would call a fast prototyping, but it's clearly still based on historic data. I'll come to this, but by the end of this talk, I would like to give you an intuition on how this can run in real time. So there's classically basically 4 steps that we do. I left out the validation part because that's the hard part. We can talk about this afterwards if you want. Let's first start on how we do this. And this will remind everyone that has done traffic models with a very classical way of building it. The big change that we do is essentially down here, which is fully automated. I mean, it's a slight bluff because we're still working on the fully, let's say, but most of what you see here is very much automated. So that means that we can offer what you just saw at a very low price, let's say, which is extremely important when you work with authorities, especially for tendering limits, etc. Now, you start out, as in every model, with some kind of network representation and with some kind of demand that you need to estimate. And how we do this here, you see here the city of Basel on your right-hand side. We work very much with openly available data. OpenStreetMap, probably most of you have heard of this. This is kind of this openly available database for mapping questions, right? And what we take out of this is the number of lanes, the turning restrictions. We also take the placement of traffic signals. And in addition to that, we put on top of the network here on these yellow rectangles, basically the sensors that the cities or the authorities provide us with. These are sensors that are installed in any way and are kind of a byproduct, let's say, or necessary for their traffic control to work. And we use basically the byproduct, which is the flows and the speeds that they record in most cases, as an input to our model. We then do a few things. We add GPS data, etc., if necessary, but essentially, the hardest part is this part here. Traffic modelers around or here will probably know that getting an origin destination matrix is one of the hardest tasks. And when we started back in the days, just to give you kind of an anecdote, right? I said, let's just skip this whole, demand generation stuff. We'll just use something from another model someone has, because most cities have some idea of origin and destinations where they come from. But we quickly realized that for operations, where it's really about, is it 200 vehicles per hour or is it 250 vehicles per hour? It requires a very precise origin destination estimation. And what we use here is, instead of going from a classical top-down idea, where we go from socioeconomics, etc., we go from the sensors themselves. So what we try to solve, and this is nothing new, this was already introduced in the 70s, essentially, the idea is to fit the sensors flows, for example, with routes in the simulator. I mean, it's clear that if you only have one sensor and if it is 300 vehicles per hour, you can find endless ways of matching it, right? But the city of Zurich, for example, has 1,800 of these sensors. That constrains your problem quite a bit already. In addition to obviously other parameters such as route lengths, distributions, etc., this constrains the model so much that in the end, if you look at this left-hand side, where we were lucky enough to have measured origin destination, so this is an origin, it goes to here, etc., a chord diagram, and you compare it with the estimated one, we get a fairly good distribution already. So something that can be used very well. And the great thing about this is what you see here on the right-hand side. We try to solve this linearly, which is super important for what you'll see afterwards, is to run all of this in real time. because only this way, or at least to our opinion, this way you can solve it very quickly for every hour to come. And the greatest thing about this is you get an everyday origin destination matrix and not just one for, let's say, an average day, which is what usually transport modelers work with. We then use a software-independent simulation, which for us is Sumo. Has been mentioned quite a few times today already. I think it's a very cool tool. Essentially, it's developed by the German NASA, the DLR, right? And it's a physics-based model. What you see here is our model that we developed for the highway authorities of Switzerland, which here we're zooming into an intersection, a highway intersection north of Lucerne. This is the Lake of Lucerne that you can kind of see here. And all the vehicles and the whole simulation that we built here was built only based on data that they already have. So they didn't have to buy any additional data, no TomTom data, no here data, etc. And this replicates speeds and flows very well. Now, in a second step, basically, there's one more step to do in the calibration process. It's once you have origin destinations and you have your network, what you also need is to calibrate inter-vehicle parameters. And these inter-vehicle parameters, that could be, for example, the time gaps between the cars, the accepted time gaps, etc., kind of microscopic parameters. And what we do here is we use parts of my PhD, which was the MFD itself. So this kind of macro view of cities. We first kind of divide the city into different regions, which are more or less homogeneous, and then find in a second step, I'm sorry about the resolution of the second picture, which shows basically MFDs, so these kind of macroscopic ways of aggregating traffic inside these zones. We try to find the range of these parameters, and in a second step, in a street level calibration, we break it down to the actual micro level. So this brings me to the last part of this presentation, which is the real-time integration of the scenarios and the visualization. So one important factor is really the visualization. I think it has been mentioned by many actually today, how important it is to visualize things so that people understand it at the end, right? And this is exactly what we try to do, and this is why it looks like a Google Map-ish type of overview. Now, the next step that we're trying to do is what you see here, which is really, I would say, a simple way, but not a simple thing to do. It's a simple way to show the architecture that we're trying to build behind of this. Let's imagine that you're trying to run what you just saw here in real time, and the question would be, we'd like to change the traffic signals at the outskirts of the city, just like a perimeter control that, for example, Nicholas Gerolimis talked about yesterday, which really is being proactive in terms of control, right? So proactively adapt the control, the traffic control, maybe an hour in advance. And in order to check that, what we want to do is basically have a system that can predict and simulate at the same time. And this is exactly what we're trying to do here. So imagine that you have a city that has data in a real-time API, which actually quite some cities have by now, where you can have access to that. The first thing that you do is basically, or that we do, is we determine the closest historic scenario. So we try to find what scenario is the closest from the one that we're just observing from the data. How do we do this? This is best shown in this picture, which is from my research back in the days, which essentially we found out that a city of Zurich, for example, if you look at 365 days and you analyze the different patterns that there are in the city from a traffic perspective, you can cluster them into roughly 6 to 8 clusters. And those clusters are not just Monday through Friday and then Saturday and weekends, right? It depends very much on if your Monday behaves like a normal Tuesday, for example. So you can match basically and map these elements, or let's say the real-time data that comes in. You can map that to the closest scenario you have in the background and choose that as your starting point. You basically then go on and you add and this is the first time we use machine learning approaches where we try to estimate the future flows in the next hour. How do we do this? We use, as I said, a machine learning approach which uses temporal and spatial correlations. And you see here the predictions that we do and the blue trace for the next 15, 30 minute, 45 minutes up to 1 hour for a highway section close to the Gotthard Tunnel, which is this main kind of tunnel that goes through the Alps in Switzerland. And we're doing quite okay. It's clear that we can't capture all the different stochasticity, but this allows us very much to, if you remember the previous slides, to map basically this prediction into this endogenous model, which is this bottom-up approach where we estimate origin destinations from flows only for the next hour. And so essentially that allows us to calibrate or to essentially have a model which has a simulation with management strategy that can forecast in the next hour, right? The next few hours, maybe 1 to 2 hours. And then you can basically start and double check whether you should turn on your parameter control in the next hour already, or rather wait a little bit. And this process is a rolling horizon process. We implemented this, or at least a version of this already for the Gotthard, as I just mentioned, which is this alpine tunnel. And here the highway authorities, what they would get is the prediction of what would happen in the next 2 hours with different management strategies. And this would also basically tell them when to do something. You know, obviously green means that they don't have to do anything, and so on, etc. And this would allow them to manage traffic in a much more proactive approach. The last slide is the thank you slide. This presentation would have not been possible without all the co-workers at Transcality, so I would like to thank them as well, and thank you for your attention, and I'm happy to answer any questions.